because Approx-Vertex-Cover is a greedy kind of algorithm, greedy method. Line number 4 is important because any edge I can pick here. There is no boundings, arbitrary. Arbitrary means randomly I am choosing. Anything I am entitled to choose any edge. There is no boundings. And then accordingly you are getting the results. So they have chosen BC first. So once they chose BC means this will be deleted, this will be deleted, and this will be deleted from the set E dash. E dash is initially, let's say it is having BC, BA, and then CE, and then CD, EF, ED, DG. Now you have to choose edges from here. So this random choice, line number 4 will happen from this E. Now they have chosen initially BC. So they are saying that BC has been chosen. No problem. Let us choose BC. So that means what? That means BC has been chosen here. So BC is gone. That means this. So BC you can remove from here and you can keep it in C. BC they have chosen, and then they have chosen EF. Yes, no? EF. So EF. So BC if you choose means BA will be initially BA will be deleted, and then CE will be deleted, and CD will be deleted automatically, because these are all, this is the vertex cover. So BC is covering this, so all will be deleted. This will be deleted, this will be deleted, this also will be done. And then they are choosing EF. So EF means this will be deleted and this will be deleted. So that means ED will be deleted, and then FD will also will be deleted. What is FD or DF? What is FD? Huh? This is DG. DF. So DF will be deleted. So then my set Approx-Vertex-Cover set is having BC and EF, and then finally you are choosing DG. Once you choose DG means this will be included. So this is my vertices. So how many vertices? B, C, E, F, 6 vertex. But optimally, if you look at this graph, how many vertices are minimum required? Optimal solution. So this is Approx-Vertex-Cover solution, capital C. Now what about C star? That is the optimal. Optimally, how many vertices should have participating? Optimally, they are saying that these are the vertices should participate, B, D and E. That means your algorithm should have written this optimal algorithm where you are getting B, D, E. That means B and then D and then E. They are saying these 3 vertices are enough to cover this whole graph. It is true only. B will be covering this and this. They will cover this and this. E will cover this, this and this. And D will cover this. D will cover this and this and this. So 3 vertices are enough. So optimally it is 3. That is nothing but B, D, E. That means B, D, E. So this is 3. Optimal should have been. I don't know which algorithm. Okay, we don't know what kind of algorithm it is. I mean, you don't know. They have chosen something. But Approx-Vertex-Cover we know. Approx, what is the time complexity here? Only one for loop. Line number 3. So one for loop, line number 3 means how much time complexity, students? Linear. Only one for loop. Maximum time complexity is here. That's why big O of V plus E. Linear time, Approx-Vertex-Cover. Not optimal. But this is optimal, which is you don't know which kind of crazy algorithm nobody is able to write. This is not able to write in polynomial time. Now let us go to the proof. Proof says that Approx-Vertex-Cover is a polynomial time to approximation algorithm. This is the proof. Polynomial time to approximation algorithm. Meaning is what? The algorithm that we have written here, Approx-Vertex-Cover, this algorithm is time to polynomial. That means it is time to polynomial in the sense we got the optimal solution which is 3 vertices according to the given graph. Approx vertex cover got 6 vertices. So this 6 is 2 times behind this optimal, because 6 is nothing but 3 into 2. That is what this algorithm says. But this algorithm, which is of 3, nobody is able to write. No one able to write this algorithm in polytime. But because it is a small graph, with eyes we can check. The really BDE is actually BDE, right? Students, BDE or not? Say yes or no. This BDE should be the result. But this is not happening in polynomial time. That is a crazy thing. This is happening in polynomial time, but this is not good because it takes 6. Number of vertices are less, but even the number of vertices are 7 or 8. This takes 6 many number of vertices. This takes 3. But this algorithm nobody knows. That is the thing. So this is the NP complete problem. Now the proof. What this proof said. Minutely you have to read it. Okay. This proof says. So the set C of vertices that is written by the Approx-Vertex-Cover is a vertex cover since the algorithm loops until every edge of G has been covered. That means all edges have to be covered. That is true. First paragraph is true. Second thing, to see Approx-Vertex-Cover returns a vertex cover that is at most twice the size of the optimal. So optimal is this 3, twice the size is 6. Let A denote the set of edges that line number 4 of Approx-Vertex-Cover picked. What they try to say, I'll just simply. So we understood what is vertex cover in last class. So we had a greedy algorithm. So this is Approx-Vertex-Cover. So in this Approx-Vertex-Cover, what happens every time we pick any arbitrary edge from the graph. Which graph? This graph. Arbitrary edges we are picking. So first edge was BC, second edge is EF, and third edge is DG. So total we have picked. So once you pick BC, then the adjacent vertices and edges, that means B's adjacent vertex is A and adjacent vertices of C is D and E. So we used to delete these edges. So in our set we used to cover which vertices? BC. Then once we have BC, then this edge and this edge, and these 3 edges will be deleted. So remaining graph will be this much only. Yes or no? From this graph, again any arbitrary edge you can pick. Let's pick EF. Once you pick EF, then the adjacent vertices or adjacent edges, adjacent vertex only, this one, adjacent vertices, this one will be deleted. Once you delete these 2, then you add it here in your graph, which is what? Which we call C. This is C. Every time I am adding this UV here. So initially my C is empty and then I am keep adding here. After EF, you will be left with this graph. Then you pick DG, because once you pick EF, then this is already deleted. This one will be deleted. This one will be deleted. So DG. So this is minimum vertex cover considering Approx-Vertex-Cover algorithm. Time complexity is very simple. You have only one while loop which will maximum generate V plus E. V go of V plus E will be the time complexity, which is linear. Because only one for loop is there. Yes or no, students? One for loop can generate maximum N. So it is linear, no problem. Time complexity is linear, so it is not exponential. But whether it is optimal, it is not optimal. Why? Because optimal vertex cover from this graph is which one? D, let's say B. B means this one if you pick. B is connected to this and this. Then you pick D. D is connected to this, this and this. And then you finally and this also. Correct, friends? And then finally you pick E. Very good. This is my optimal vertex cover. How do you find it? Visually looking at the graph, you have found it. That means there must be some algorithm. But that algorithm unfortunately is not in polynomial. Here why you are able to do, you can ask me, sir, then how can I find it? Because number of vertices are very less. 8 vertices, 1, 2, 3, 4, 5, 6, 7. 7 vertices, 8 edges. Visually you are able to figure it out. Once the number of vertex increase, you won't be able to write any algorithm that will give you such kind of optimal result. It's a minimization problem or maximization problem? Minimization problem. So your result, which is nothing but 3 vertices, 3 vertex here. But unfortunately here how many vertex? 1, 2, 3, 4, 5, 6 vertex. So this is much more than these 3. But this algorithm is not available. That visually that we have seen and we have figured it out. That is not available in polynomial and nobody has done yet. You can see 6. Now you can easily see that 3 and 6, 3 into 2 equal to 6. Okay. So what is the rho here? Approximation ratio rho is nothing but 2 you can call. Your solution, which is 6, is 2 times worse than the real solution. Yes or no, student? 2 times bad than the real solution. But real solution is not available in polynomial. This is Approx-Vertex-Cover. You will be somewhat happy because you totally have how many edges? 1, 2, 3, 4, 5, 6, 7, 8 edges. Here how many edges you got? 6 edges. 2 edges you have reduced, which is okay. But vertices, you are how many vertices? 1, 2, 3, 4, 5, 6, 7 vertices. But here you have 6 vertices. Yes or no, students? So 7 compared to 7, 6 is somewhat okay. If you increase the number of vertices, you will get somewhat better results. So in this graph, it is almost like taking the whole graph. All vertices almost we have covered. Yes or no? But this is what the best thing available right now, which is called Approx-Vertex-Cover. Now, 3 into 2, which is 6, approximation ratio is 2. So now if you Approx-Vertex-Cover is a polynomial time to approximation algorithm. This is the theorem. Theorem 35.1, which is just now I explained, nothing here. Just now I explained that 6 is 2 times worse than 3. So Approx-Vertex-Cover, your solution, which is 6, is polynomial time to approximation algorithm. Meaning is it is 2 times lagging than the actual real solution. Clear or not? But this is like having theorem should be provided. So we have already shown that Approx-Vertex-Cover runs in polynomial time. The set C of the vertex that is returned by Approx-Vertex-Cover is vertex cover since the algorithm loops run until every edge is G, which is true. If you see this algorithm, this is let U be any arbitrary edge from E dash. That means E dash is your graph. You pick any arbitrary edges and then include it. Just that you have to do what? You have to delete the remaining adjacent edges. If you pick BC means you have to delete this and this. That is what it says. E has been covered by some vertex in C. To see Approx-Vertex-Cover returns vertex cover that is most twice the size of the optimal cover. So twice the size of the optimal cover means what? Just now I explained. Optimal cover is giving result 3. Your result is 6. So 6 is twice the optimal cover. Yes or no, students? In order to cover the edges in A, any vertex cover, in particular optimal cover. So let's call this optimal cover as C star. Okay? Let us call this. Or in fact, we can, what it says. In order to cover the edge in A, any vertex cover in particular, an optimal cover C star must include at least one endpoint of each edge in A. Now let us see what is A. What is A? Capital A. In order to cover the edges in A, any vertex cover, in particular an optimal cover C star. What is A here? Let A denote the set of edges that line number 4 of Approx-Vertex-Cover picked. That means line number 4 of Approx-Vertex-Cover is this one. Yes or no, students? So whichever edge this line number 4 is picking, that is, let's say, capital A. So how many edges it is picking? First it picked BC, students, yes or no? Then it picked EF, then it picked DG. This is Approx-Vertex-Cover. For that you have picked arbitrary edges. So A is basically, once this while loop fully executed, your A will be equal to same thing BC, comma EF and DG. Do you agree or not, students? Clear? In these three edges, how many vertices are participating? 6 vertices. Very good. Now let us go to the point. What it says. So it says that in order to cover the edge in A, that means now your optimal cover. What is your optimal cover? Let's call it C star. Here how many vertex? 6 vertex. What about C star? Which are the vertex we choose for optimal cover? B, D, E. Very good. This is my C star, which is nothing but 3. So what it says? C star must include at least one endpoint of each edge in A, which is true only. You see, this is your A. So C star, this is the C star, B, D, E. What it says is that C star must include at least one endpoint of each edge in A. That means this is my first edge BC, this is my second edge EF, this is my third edge DG. At least one endpoint. So that means what? That means you have something like this. You have BC here. Correct, friends? So BC, at least one endpoint which was B. So B is covered here. C star will cover that. And then EF. EF means this one. At least one endpoint of EF is which one? E. This is my E. This is my B. And at least one endpoint of DG is D. Clear or not? This is correct. This is you understood. No two edges in A share an endpoints. No two edges. No two edges in A share an endpoint since one edge is picked in line number 4. All other edges that are incident on its endpoints are deleted from E dash in line number 6. So no two edges in A share an endpoint, which is also true. So this is my BC, EF, DG. Any edges sharing its endpoint here? Just look at it minutely. BC is one edge, BC, which is BC. And then second edge is EF. Third edge is DG. Whether endpoints are shared? No, no. They are all independent independent edges where no endpoints are shared. That is what it says, which is true. Again, this statement is also true. No two edges in A share an endpoints. Since one edge in A, one edge is picked in line number 4. All other edges that are incidents on its endpoints are deleted from the E dash, which is true. Thus, no two edges in A are covered by the same vertex from C star. No two edges in A are covered by the same vertex from C star, meaning that every vertex in C star, this is every vertex in C star. That means every vertex means B, D, E, each vertex in C star, there is at most one edge in A. You agree or not? Every vertex C star B, for this vertex B, there will be at most one edge. BC is there, at most. Every vertex in C star, which is D, there will be at most one edge in A, which is DG. Every vertex in C star, which is E, there will be at most one edge in A, which is EF. So that means this statement also correct. So there is at most one edge in A. Given the lower bound C star greater than equal to A on the size of an optimal vertex cover. C star greater than equal to A on the size of the optimal vertex cover. Now this statement is in terms of size of the optimal vertex cover. So you have to be a little bit careful. Size of the optimal vertex cover. So size of the optimal vertex cover, from the optimality point of view, C star is having 3. Correct, friends? Size point of view, what is the A? 6. So which is optimal? 3. That means from optimal point of view, I can say this is the situation. C star is greater than equal to A. Optimal point of view, it is better. C star is better. The meaning here, they try to say that on the size of an optimal vertex cover, C star is greater than equal to A, which is true only. C star is greater than equal to A. So modulus, if you take mod means what? Mod means the number here. How many vertex? 1, 2, 3, 4, 5, 6. How many vertex? Mod of C star? 1, 2, 3. So from that optimality point of view, C star is greater than equal to A. Each execution of line number 4 picks an edge for which neither of its end points are already there in C. Now one case will be there, like once we are deleting these edges, so each execution in line number 4 picks an edge for which neither of its end points are already in C, yielding an upper bound. Now another interesting thing is that what is C will be equal to twice into A. If A is the edges, so maximum what happens? If you pick one edge, this is one edge, right? A to B. For one edge, how many vertices participate? 2 vertices. For n number of edges, how many vertices will participate? Twice n. For a number of edges, complete thing, if you pick all edges, then how many vertices? Twice A. First case scenario, C equal to twice A. Now what they are saying, C equal to twice A. Now here A is actually less than C star. This is equation number 35.2. This is equation number 35.3. Correct, sense? So just replace this A with C star here, because here A is nothing but less than equal to C star. You agree or not? Just writing the things, just shuffling. A is less. So here you replace it. Twice A is less than C star. So twice A also will be less than C star. Twice into C star. That means your C, which is your thing, worst case, is twice less than the optimal cover, which is called polynomial time to approximation. Clear or not?